Okay, so let us now see this one. So here we are given a ring R and M2R, which denotes the ring of all 2 by 2 matrices where the entries are coming from R, and the operations of course are matrix addition and multiplication. We have to explain why these two rings R and M2 of R have the same characteristic. Okay, so let's see the solution. So we are going to handle two cases, namely when R has characteristic 0 and when the characteristic of R is a positive integer. So let R have characteristic 0. So we consider that first. This means that there is no positive integer n for which nx is equal to 0 for all elements x in R. This will not happen. That's what being of characteristic 0 means. So now our aim is to show that the matrix ring also has characteristic 0. Suppose that is not true. Suppose the characteristic of M2 of R be a positive integer n. So that means n is first of all a positive integer for which n dot x is equal to 0 for any x coming from M to R, and n is the least such positive integer. That's what characteristic n means. Okay, so now we will be seeking a contradiction, because this is not what is supposed to happen, but we have supposed that. So now we are trying to get to something wrong. Then for any element A in the original ring R, we have this n dot A. This 2 by 2 matrix will be equal to the 0 matrix. I should have this is looking a little bad. Let me write from here. And this equation is a consequence of the fact that the characteristic of this has been supposed to be n, and which implies what? It implies that n dot A, n dot A, n dot A, n dot A, this is equal to the 2 by 2 0 matrix, and that in turn implies that n dot A is equal to 0. You should note carefully that this A is not an ordinary number. It's a ring element. Just like that, this 0 is not the number 0, not the integer 0, but the 0 element of the ring R. And you of course understand also that due to the nature of matrix addition, n dot this becomes this. For example, 2 dot AAAA means what? Adding 2 copies of this matrix, which gives us A plus A, A plus A, A plus A, A plus A, and each such A plus A ultimately means 2 dot A. So that's why. So we now get this. But then what does this equation tell us? It tells us that we have got one positive integer n such that n dot A is equal to 0 for every element A in R. So the characteristic of R cannot actually be 0 but will be some positive integer. Maybe not this n itself but something less than or equal to this n. But it will be finite. And that contradicts the this first supposition, first assumption actually, first hypothesis that R is of characteristic 0. But this implies that R has a finite characteristic. Finite characteristic means non-zero characteristic, a contradiction. So our supposition, that supposition is wrong, i.e. this cannot be a finite characteristic like what we have supposed. So this must have characteristic 0. So when R has characteristic 0, then this one also, M2 of R also has characteristic 0. Next, let R have so now we are considering the other case where R itself has finite characteristics. Characteristics say M, where M is some positive integer. Okay, so now our aim is to show that M2 of R also has characteristic precisely M. For any element in M2R, which is again a 2 by 2 matrix with entries coming from R, first we are going to note this fact: M times A, B, C, D. Because M is a positive integer, this equals MA, MB, MC, MD. But because M is the characteristic of R and A, B, C, D, these are elements coming from R, So all of these are equal to the 0 element of R. This shows that M times any element from M2 of R is the 0 element of M2 of R. This itself does not tell us that the characteristic of M2 of R is M. It only tells us that it has a finite characteristic, which is a positive integer less than or equal to M. Now we need to show that this characteristic cannot actually be less than M, but it should be equal to M. So now we are going to suppose that, say, the characteristic is actually less than M, and again arrive at some contradiction which would show that it has to be equal to M. Suppose that, okay, but before we make this supposition though, let us conclude that hence this has finite characteristic. Okay, now let us make that supposition. Suppose the characteristic of M2 of R is N. Well, you can use something else also, say T, where T is a positive integer satisfying this. Say we now have this supposition, and now we want to again arrive at something that is wrong, which will prove that our supposition itself is wrong. Now, for any A in R, we have T times A equal to this. And where is this coming from? This is a consequence of the fact that T is the characteristic of this, and this 2 by 2 matrix, all of whose entries are equal to A, is an element of M2 of R. So T times this will be equal to the 0 element, the 0 matrix. But now what do we get from this? And that implies that T dot A is equal to 0. But this cannot be, because according to our hypothesis now in this second part, M is the characteristic of R. So T dot A cannot be equal to 0 for all elements A in R for a positive integer T less than M, because M being the characteristic has that property, and at the same time it's the minimum possible positive number having that property. So that is the contradiction. but this contradicts the minimal nature of M. Within brackets you can also write as the characteristic of R. So that means our last supposition is wrong. i.e., no such positive integer wait, what is the exact supposition that we made? That let the characteristic of M2R be T. Okay. That is, the characteristic of this cannot be T means what? It cannot be less than M. But we already have seen that M times anything from this string is equal to the 0 element. Hence, the characteristic of M2 of R is equal to M. Is M. And that's it. So we have managed to show that these two rings R and M2 of R have precisely the same characteristic. Next. Let R be a ring with M elements. That means R is a finite ring in which the number of elements is n. Show that the characteristic of R divides M. So let's see how that happens. Let the characteristic of R be N. Okay. Then, since N is the characteristic, N is a positive integer. So what's important here is that N is a non-zero integer. And that is why using the Euclidean algorithm we can divide m by n to get a quotient and a remainder. Then there exist integers q and r such that m is equal to qn plus r, so that q is the quotient and r is the remainder, where the remainder of course satisfies these inequalities. We already know this thing. Okay. Now for any element a in R, we have, so you know, let me just do the calculation and then I will explain. Let me continue writing just like that. 0 is equal to m dot a, which is equal to qn plus r dot a, that is equal to q dot n dot a plus r dot a, and that is equal to r dot a. Okay, just give me a moment. Okay, so what we have done here, we have considered any element a from the ring, and then we are writing that m dot a is equal to 0. What is this? You see, the ring is a group under its own addition. We already know this. And because the ring has m elements, this is a finite group. So in this finite group, we have Lagrange's theorem, and in particular, we have that corollary to Lagrange's theorem which tells us that if we raise any element from this group to the power where the exponent is equal to the order of the group, then we are going to get the identity element of the group. This is one consequence of Lagrange's theorem from group theory. Now this equation, if you think of it in this additive group of the ring, it looks like this. Because 0 is the identity element here, and because the group is additive, this mth power of a is m dot a. That's how we write it. So that's how we are getting 0 equal to m dot a, and m is of course qn plus r, so qn plus r dot a. But then how is this equal to this? That comes from the rules of exponents that are there in any group. So if I write this thing using multiplicative notation in this group, then it will look like this. And you do understand that here between these two factors, if I call these things factors, or these two elements, the qth power of a to the power n and a to the power r, we have the binary operation of the group. Because that operation is plus, we have plus here. So this step uses the rules of exponents. In fact, both of them, because you need a to the power qn equal to a to the power n to the power q. That is one rule, and this plus distributes like this, I mean the exponent gets distributed over the base like this. So that's what we have used here. Okay, now how is this equal to r dot a? For that this has to be 0. This is 0. Why? And that comes from the fact that r has characteristic n. So n dot a is 0 and q dot 0 is 0. But you see, why is q dot 0 0? That is because this element in this group is actually this, the qth power of the identity, which we know regardless of the integer q, whether it is positive or 0 or negative, it is going to be identity. So that's why it is 0, and that's how we are getting this thing. But now what can we say from this equation? We know that n being the characteristic of r is the smallest positive integer, such that if you take n dot a, you are going to get 0 for every element a in r. But here we are getting r dot a equal to 0, and r is already less than n. So in this situation, if r also becomes a positive integer, then the minimality of n is violated as the characteristic, and that cannot happen. So r cannot be positive, r has to be equal to 0. And we can write like this: due to the minimal nature of n, this implies that r is equal to 0, i.e. m is equal to qn, and that's it. That is why the characteristic of r, which is n, divides m. Divides the number of elements in the ring, if the ring is finite. Next, explain why a finite ring must have a non-zero characteristic. You may or may not have noticed that the previous solution leaves one question unanswered. We had to show that the characteristic of R divides M, the number of elements. So what we did, we immediately assumed that the characteristic of R is a positive integer n. But why? That is the question that was not answered here. So in that sense, this solution actually is incomplete. That will now be answered. explain why a finite ring must have a non-zero characteristic, because someone can argue that okay, you are going to consider the characteristic of R in spite of the fact that R is finite, say the characteristic is 0, then there is no question of dividing by 0 and those things. But that is not going to happen. Why? That will now be clear. And let's see the solution. Let R be a finite ring with m elements, since R is an abelian group. Actually, there is no need to mention abelian group here for this, but still I mention, it's just a fact. Since R is a group under addition, we have, again using that corollary to Lagrange's theorem, the mth power of any element in R is going to be equal to the identity element, and writing that fact, expressing that fact as an equation, keeping in mind that R is an additive group, that becomes this: m dot A is equal to 0 for all A in R. But if we are getting this, where m definitely is a positive integer. Why is m a positive integer? Because m is the number of elements in R, and m cannot be 0 because R as a set is non-empty. The empty set is it's not a ring. So if this is happening for some positive integer m, then a least such positive integer also would exist, due to the fact that the natural numbers are well ordered, so that least element always exists in any non-empty subset of the set of natural numbers. So that is why we can write, hence there exists a smallest positive integer in such that this thus the characteristic of R is n, which is a positive integer, so it's a non-zero characteristic. Now along with this, the previous solution is complete. Next, oh, I think I bumped into this. Let me see if I lost focus. No, it's okay. Okay, so the next one is computational. Find all solutions of this quadratic equation but in the ring Z3 of I or Z3 of I, which consists of complex number. I should not say complex numbers, okay, that is wrong. The elements in these are not complex numbers, but they look like complex numbers where the real and imaginary parts, if I call those things real and imaginary parts, they are coming from this finite field Z3. In place of Z3, if we have our ordinary ring of integers, then the elements will be complex numbers, which are called Gaussian integers. Okay. So now we have to find the solution. So let's take an arbitrary element from this ring, put it here and see what we get. Let a plus bi belonging to this be a solution of our equation. Yeah, okay. Then you can of course manipulate these things as if you are working with complex numbers. All the rules are similar, in spite of the fact that this a and b are not real numbers. They are just like ordinary complex numbers. The real and imaginary parts are coming from the field of real numbers. In this case, they are coming from this finite field. That's it. But the field axioms are same. So using those things, we get this a square minus b square plus 2iab minus a minus bi plus 2 is equal to 0. Now this implies minus a plus 2 plus b times 2a minus 1 times I is equal to 0. And by the definition of equality in this ring, this implies that this has to be 0 and this also has to be equal to 0. Both of these things have to be simultaneously 0. Okay, now this equation looks a bit complicated. It has two variables and also it's non-linear. But this one is not that complicated due to the fact that after all a and b, and hence the two things b and 2a minus 1 are coming from a finite field, no doubt, but a field. And since a field is an integral domain and hence lacks zero divisors, so this product will be 0 if and only if at least one of these two things is equal to 0. You have to think of these things in this manner, because keep in mind these are not real numbers. Since this is a field, this implies b is equal to 0 or 2a minus 1 is equal to 0. Now let us see first of all what happens if b is 0. If b is equal to 0, then this equation reduces to a square minus a plus 2 equal to 0. But there is no, you see, this a and b are after all coming from Z3, right? Now there is no element in Z3 that satisfies this equation, because there are only 3 elements in Z3, 0, 1 and 2. You put 0 here in place of a, you get 2. 2 is not equal to 0. You put 1 here, you again get 2, that is also not equal to 0. You put 2 here, minus 2 plus 2, they cancel, and you are left with 4. In Z3, 4 is equal to 1. Again, that is not equal to 0. But this equation, this one, has no solution A in Z3. So we cannot have b equal to 0. So if b is non-zero, this must be equal to 0, again due to this structure being a field and hence an integral domain. So we must have what is it, 2a minus 1 equal to 0. Now let us see what a can be from here. Do not foolishly write a equal to 1 over 2. Yes, you can write, but you have to know what 1 over 2 is in the field Z3. Without going into those things, you just put the possible values of a, because there are only 3 elements here, and see which one satisfies, if there is any such thing. So putting a equal to 0 gives us minus 1 equal to 0. That is not true. Putting a equal to 1 gives us 1 equal to 0. That is also not true. If we put a equal to 2 though, then we get 4 minus 1. That is 3 equal to 0. That is true in Z3. That means a has to be equal to 2. And now you go back to that other equation and see what the value of corresponding value of b is if a is 2. So from this is the equation, right? A square minus b square minus a plus 2 equal to 0. We get, if you put a equal to 2, then this 2 will give you 0, and b square will be equal to a square, that means 2 square. So b should be equal to 2. That is the only possibility. Hence, the only element in this ring that is a solution of our equation is 2 plus 2i. That is the only solution. Next, this one is also computational. Here also a quadratic equation is given. Consider the equation x square minus 5x plus 6 equal to 0. And there are parts. How many solutions does the equation have? In Z7. Find all solutions of this equation in Z8. Of this equation. In C8, then again same, find all the solutions of this equation in set 12 and then this. So because all of these rings are finite, you just have to see whether each element is a solution or not. So it's a direct search. That's just what it is. But you can still make the job a little more manageable by factorizing this polynomial. We know that, and this is a polynomial we are well familiar with from our school days, because in our first introduction to algebra, when we get quadratic equations and when we see the many methods of solving such equations, one of them is factorizing the polynomial. There this precise polynomial comes quite often. So this, you see, we may be tempted to immediately conclude that the only two solutions are 2 and 3, but that is not quite true. Never forget that these are not systems in which we have real numbers. These are something else. 2 and 3 are solutions, but there may be others also. 2 and 3 will be the only solutions if you are in a field or in an integral domain, again due to the absence of zero divisors, which is what happens in the system of real numbers. But these are not all fields. For example, this is not a field, this is not an integral domain, this is not an integral domain, this is not an integral domain. Only this one is a field due to the fact that 7 is a prime, but these are composite numbers. So there we have non-zero zero divisors. So let me just simply write down the possibilities. Since here in the first one we can use the fact that C7 is a field, or more specifically, since this lacks zero divisors, we have this is equal to 0 if and only if this is equal to 0 if and only if this. That means if you are thinking, interpreting this equation in this system, then you have this. So there are two solutions in this, and they are of course 2 and 3. Part B. In part B, the solutions turn out to be this. 2 and 3, just like this one, will be solutions, but well, in part B also it turns out that the solutions are 2 and 3. Not because of this reason, but it just happens that 2 and 3 are the only solutions. No other element other than 2 and 3 coming from Z8 solves this. Okay, so in this case also X is having this only 2 values, but that is not the case in the other rings. In part C, you have C12, and here the solutions are 2, 3, 6 and 11. And in part D, that means in Z14, the solutions are 2, 3, 9 and 10. Well, if you put, for example, say you are in Z12 and you put X equal to 6 here in this product, then you get what? 6 minus 2 is 4 and 6 minus 3 is 3. 4 times 3 is 12. So in Z12, 12 is equal to 0. That is why you are getting this extra solution, and again another one for X equal to 11. Similarly, in Z14 you have these 4 solutions. And let us finally see one more. This will be 58. Find the characteristic of this direct sum. We understand that this is the ring with 4 elements, and this is the sub-ring of the ring of integers consisting of all the multiples of 4, all the integer multiples of 4. note that for any positive integer n, we have n dot a comma b. This is an I don't want to, I did not intend to take just any b but 4. Now this is an element in this ring. We know that the elements are ordered pairs, where the first coordinate is coming from C4 and the second one is coming from the second ring, and where addition and multiplication are defined component wise. So this is going to be n dot a times 4n, because this 4 is the actual integer 4, so we can n dot 4 means 4n, and this can never be equal to 0 comma 0, which is the 0 element of this ring, regardless of irrespective of what the integer n is. 4n can never be equal to 0 if n is a positive integer. This we already know. So we see that this ring cannot have non-zero characteristic. Thus, okay, so that means its characteristic is 0. Due to this second ring, we cannot have a finite means non-zero characteristic. And let me end the video here with this one. In the next Gallian ring update, we are going to solve more. In 2 more Gallian updates on rings, we are going to complete this section, this current set of exercises, and then we will move on from there. And tomorrow, as usual, we have analysis. I think we are in the middle of answering those whys in the proof of Riemann's theorem. So tomorrow we will hopefully complete answering all the remaining whys. So that's it for tonight. So see you tomorrow with that. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.